Welcome to this video on solving right triangles. Before we get to the actual problems, see if you can follow me on this little thought experiment. Suppose I gave you a triangle, said we had a right angle, so make it a right triangle, and that one of the angles was 25 degrees. And suppose I asked you to solve for the remaining sides and angles. Well, we couldn't do it uniquely because I haven't given you enough information about this triangle to decisively solve for the other side lengths. There are just infinitely many triangles that would have a 25-degree angle in them. And think of it as you could make a very small, medium size, or large triangle, all of which would have a 25-degree angle here. The point being, if they don't give us enough information about a triangle, we can't uniquely solve for all the angles and side lengths. On the opposite end of the spectrum, by contrast, suppose I gave you a right triangle and said we have a 57-degree angle, a hypotenuse of length 10, and a leg of length 8. And I wanted you to solve for the remaining sides and angles there. Well, in this case, in some sense, I've given you too much information. And it turns out that no such triangle exists. For example, it turns out if we had a right triangle with a 57-degree angle and an 8-degree opposite leg, that the hypotenuse would have to be 9.5 to make a right triangle there. Or by comparison, let's say I said we wanted to make a right triangle whose hypotenuse was 10 and side length was 8. It turns out that the angle opposite the 8 would be 53 degrees approximately and not 57. Or suppose I gave you the task of finding the information for a right triangle whose hypotenuse was 10 and who had a 57-degree angle. Well, it turns out the side opposite the 57 degree would be 8.4, not 8. So the picture as shown now is not even a buildable triangle. No such triangle exists. And the point of looking at these two triangles is to realize that if I specify, as on the left of the screen, if I don't specify enough information, there's more than one triangle to match that description. And if I specify too much information, as seen on the right, then there may not even be a triangle that exists that matches that description. The situation that this video is about is where we're given a right triangle, and we're given generally two pieces of information, or if you count the 90-degree angle, 3 pieces of information. Because in this case, almost always, there is one unique right triangle that matches this description. And it's our goal to therefore find the other 3. It turns out there is exactly one right triangle, with a 20-degree angle and a hypotenuse of 12.3. And our job, and what this video will teach, is how to find the remaining sides and angles of this triangle. And it turns out, if you do the math, which this video will show you how to do, so I don't expect you to know it yet, but if you do the math, then we can find the remaining sides and the remaining angle as shown here. But before we get into the actual problems that we're going to look at, it's also worth noting that it's almost never the case that the triangles are drawn to scale when you're given them in a mathematical problem. There's 2 reasons for this, but before I give those, let me just show you what I mean by not to scale. This side here that you see with the green arrow, if that side has a length of 4.2, then just visually speaking, looking at the hypotenuse, it really wouldn't make sense to say that that side had a length of 12. I mean, it's not physically not triple the size of the height. And so don't expect your pictures to be to scale here. Then the 2 reasons are this. One, as math teachers and professors, we don't necessarily want to sort of give a hint as to what the answer might be by drawing a perfectly scaled diagram, lest students may not feel the need to do the actual mathematics. But more importantly, when you get to calculus, which many of you will someday, the diagrams are never drawn to scale because they tend to represent things that are changing. And if you're going to draw a static or stationary picture of something that's changing in size, then you can't really expect it to ever be to scale if the thing is moving or changing. Nonetheless, you should expect your diagrams not to be to scale, and don't necessarily judge your answers based on the appearance of the picture in the problem. Here's an actual scale drawing of this triangle just to give you a better sense, and you can see that the hypotenuse is about triple the height, and this makes more physical sense. But again, this is something I've done just to show you the scale. Don't expect your pictures to be so. So here's the first problem that we're going to solve. And we're going to do 4 altogether, but for the first one, I'm going to go very slowly and methodically through a process that you can do to solve for the missing sides and angles. The first thing you want to do is name everything you don't know. So I've named my 2 unknown sides x and y, and I've named my unknown angle theta. It's traditional to use Greek letters for angles. You don't have to do that, of course. And now that I've named everything, I like to label which side is the hypotenuse, and I also like to label the legs as opposite and adjacent to particular angles. So the x, the side I've labeled x, is called the hypotenuse. It's the one side that does not touch the 90-degree angle. In terms of labeling the legs, the 15 and the y are both opposite legs depending on which angle you're referencing. You'll notice that the y is opposite of angle theta, whereas the 15 is the opposite of the 20-degree angle. You can think of opposite as being the one side not involved in the formation of that angle. For example, the side lengths x and y form the 20-degree angle. The 15 does not, and therefore is the opposite of the 20. For each leg of the triangle, the adjacent leg is the leg used in the formation of that angle. So, for example, the 15 we would say is adjacent to, you can think of that word as meaning next to. The 15 is adjacent to the theta, and the y is adjacent to the 20. My third step is to write out all 8 equations for right triangles. There are a total of 8 equations that you can use when solving a right triangle, and when you're brand new at this subject, I recommend writing out all 8 of them. Here's how to write out all 8 of your equations for a right triangle. 6 of them will come from the trigonometric ratios sine, cosine, and tangent. And if you've heard of those from your mathematics courses before, then you're familiar with sine, cosine, and tangent. If not, suffice it to say for now that they're just trigonometric functions that you can find on your calculator. And you can set up the ratios as shown here using the opposite and adjacent legs and the hypotenuse. So here are 3 equations written out for the angle theta, but here are 3 more equations written out for the 20-degree angle. And these will be the formation for 6 out of our 8 equations. The 7th equation is the Pythagorean Theorem, leg squared plus leg squared equals hypotenuse squared. And the 8th equation is a fact that the angles of any triangle, not only right triangles, but the angles of any triangle must always add up to 180 degrees, and that makes our 8th equation here. But the equations on the left, the 6 ones with trigonometric functions in them, are not really finished yet because I have to plug in what the opposite, adjacent, and hypotenuse is for each case. I'm going to show you those and recommend that you hit pause and see if you can analyze how it is that I was able to plug in the x, y, and the 15, basically the side lengths, into each of those. Go ahead and hit pause now and see if you can figure out where that came from. If you were able to figure that out, great. If you weren't, if it's a little unclear to you still, the best thing that I can say is that we plugged in the hypotenuse, the opposite, and the adjacent for each of the given angles and wrote out the equations that way. But here we have the 8 equations that apply to this triangle. Now we don't want to solve 8 equations every time we do a problem like this, nor should we necessarily. But a lot of students have trouble in the beginning using these equations, and so in the case that you're ever struggling and not knowing what to do, I recommend writing out all 8 equations. As you progress through the problem and try more and more of these, and I'm sure your teacher or professor will be giving you problems to try, you will start to hone your skills and you'll start to write out less and less equations, and you'll start to get a sense for what you should write out when. And you'll use some of the 8 equations and not all of them. And that's the ultimate goal, is to get to the point where you look at a problem and know what to write. But in the beginning, there can be a little fuzziness in the brain about what to do to start a right triangle problem. And when there's any kind of confusion at all, my best advice is start out by writing all 8 of them. But once you have, you definitely won't solve all 8 of them. First of all, because we don't need to. We only need to know, if you look at the diagram, we only need to know what x, y, and theta are. We don't need 8 equations to solve for 3 things. But more importantly, some of these are just not practical. Now, while all of these 8 equations are true, what you're going to do is basically solve any of them in any order until you know all the information you're trying to find out. In this case, x, y, and theta. And more specifically, you're going to want to discard any equations with 2 or more unknowns in them. I'm going to turn them all pink here if you can see the colors. And what you'll notice is that many of these equations have 2 unknowns in them. That some have an x and a y, some have an x and a theta, some have a y and a theta. And while these equations, if you see them in pink here, these equations are definitely true and they're not wrong, they're also not that helpful, because while we could solve for one variable in terms of another, we couldn't solve for any of these variables or unknowns numerically. So I'm going to discard the ones that have 2 variables in them and focus just on the remaining 3. We're going to start solving these now for x, y, and theta. We'll start with the easiest one, which is on the right. It doesn't take a lot of algebra to find out that theta is 70 degrees just by subtracting 20 and 90 from both sides. That I won't go into a lot of detail about. But let's take a closer look at the 2 equations on the left and center, starting with the one on the left. In order to solve the one that says sine of 20 equals 15 over x, I'm going to do a trick called cross-multiplying for proportions. To make this look more like a traditional proportion, I'm going to put the left side over 1. We've all known since 4th grade that anything divided by 1 is itself, so this is definitely a legal mathematical move. And it makes the equation look nicer in the sense that I can now cross-multiply in the diagonal sense. So when you cross-multiply diagonally, you get x times the sine of 20 equals 15. Now remember, we're trying to solve for x here. And so you could now divide both sides of this equation by the sine of 20, which would lead us to this. Now the sine of 20 turns out to be a decimal that you can find on your calculator. I'm working on my calculator right now. You can't see it on the screen, but it turns out that the sine of 20 is, let me make sure I've got it in the right mode here. I do not. Make sure your calculator is in degree mode. Calculators also have something called radian mode for angles, which you want to stay out of for these problems. So typing in the sine of 20 degrees, it turns out to be 0.342. I didn't put that on the screen because you can type this whole thing into your calculator all at once. If you type 15 divided by the sine of 20, you'll get approximately 43.9, and that lets us know what x is. So remember, the sine of 20 is a decimal, and 15 divided by that decimal worked out to be approximately 43.9. Finally, let's go about solving for y the same way. Look at the equation in the middle. If I write the tangent over 1, I can then cross multiply easily. And once having cross multiplied, I can divide both sides by the tangent of 20. The tangent of 20 is also a trigonometric function and is a different decimal than the sine of 20, of course. I won't put it on your screen there, but the tangent of 20, when worked out on a calculator, turns out to be approximately 0.364. And 15 divided by that decimal, or 15 divided by the tangent of 20, works out to approximately 41.2. And after writing out all 8 equations and deciding which 3 to use, what we now know is the values of the sides and angles that we wanted to know. It's traditional to round side lengths to the nearest tenth and angles to the nearest whole number, and so I think that rounding will suffice, and that finishes our first of 4 problems. Before we go to our second of 4 problems, I want to take a closer look at the 3 trigonometric ratio formulas we saw earlier in this video. As a means to help you remember these formulas, mathematicians have focused on the first letter of each word in them and made kind of a silly acronym, if that's the right word, out of it. And for this reason, you can see here, when mathematician says we're going to use sohcahtoa to solve a problem, which isn't a real word, of course, just a made-up one based on the order of these letters. When mathematician says that, they really mean that we're going to use the 3 formulas so, ka, and toa, or one of them at least, to solve a problem. So if you ever wondered where the phrase sohcahtoa came from, it came from these formulas. If you're hearing it for the first time, well, now you'll know going forward when a math teacher says sohcahtoa what they mean. All right, let's take a look at this problem here. Let's go through the steps. Step 1, label everything you don't know about the triangle. This time I've used different letters than the last problem, you'll notice. Step 2, write out all 8 equations. But I'm going to modify that a little bit here and show you how you don't have to necessarily write out all 8 equations, although you certainly can. Before I do that, let me label all the sides here. 10 is the hypotenuse, the side not touching the 90. K and M are both opposite legs to a particular angle. K and M are also adjacent legs to the other angles. And now, when I write out equations, I don't necessarily have to write out all 8 of them. Suppose that you were to just write down one of them randomly. The tangent of 43 is the opposite over the adjacent. This is definitely one of our 8 equations. And what you can do is just try a random equation out of the 8. There's no particular reason I started with tangent. And if writing down that equation leads to 2 variables, then erase it and pretend it never happened. Keep doing this rather than writing out all 8 of them until you have success. Here's an example of one of the 8 that is actually helpful. The sine of 43 is opposite over hypotenuse. Notice by writing out this equation, I only have one unknown in it, and that's m. So rather than writing out all 8 equations, once you get a little better and you've practiced that for a while, you can just start writing down random equations out of the 8 until you get equations that have one variable in them. Okay, and that's what I've done here. And because I sort of lucked out and got one variable or unknown in this, I'm going to use it to solve for m. I'm going to put a 1 under the m, cross multiply, And notice here that I've already solved for m by cross multiplying, so all I have to do is now find out what the sine of 43 is and multiply that by 10. It won't show up on your screen, but I have a calculator in my hand here, and it turns out the sine of 43 degrees is approximately 0.682. So if I do 10 times that decimal, or 10 times the sine of 43, I'll get approximately 6.8, at least rounded to the nearest tenth, and I now know what m is. And you'll notice here I didn't have to write out all the equations to find it. Here's another equation I wrote down. Using the 43-degree angle, I did cosine equals adjacent over hypotenuse, and I found another of the 8 equations that only has one unknown in it. If you're a little confused at this point as to how it is that I'm picking the equations, and you ever find yourself confused in solving your own problem, go back and write out all 8 of them, and then cross out the ones that have 2 or more unknowns in them. But eventually you want to get to the point where you're just writing out an equation and finding it has one unknown and using it to solve. If the randomness of that feels a little uncomfortable, then by all means write out all 8 of them, as we did in the first problem. So here I have an equation with one unknown in it. I'm going to put a 1 under the trig function, cross multiply, and notice I've already solved for k here. So I just have to use a calculator to find out what the cosine of 43 degrees is. I'm doing that on my calculator now. It turns out to be 0.731 approximately. So 10 times that decimal, or 10 times the cosine of 43, works out to be approximately 7.3. And now I have an approximation for k. Lastly, in order to find beta, I'll use the easiest equation of all, the fact that the angles of any triangle have to add up to 180. Subtracting 43 and 90 from both sides, work not shown here, but subtracting 43 and 90 from both sides will let me know what beta is. And I now have all the side lengths and angles of this triangle. Now we're going to look at a situation that's a little bit different in that we weren't given an angle in this problem to solve with. We know that we have a 90-degree angle, and we know 2 sides of the triangle, but we don't have an angle to effectively use as we had in the previous 2 problems. But it doesn't stop us from doing the same process and using our 8 equations. So I'm going to call my 2 angles theta and alpha. Again, I use Greek letters, you don't have to. And I'm going to call the unknown side length L. But before we start, let's label everything. Well, actually, let's use the Pythagorean Theorem here before we start. This is one equation that we can very effectively use when we know 2 sides of a right triangle. And when you work this out using the Pythagorean Theorem and a calculator, you'll find that L, or the hypotenuse in this case, is approximately 7.4. So what we've managed to do here is find one of the sides right away without even using sines, cosines, or tangents. Now what I can do is make up another one of the 8 equations. I picked theta for no particular reason and tangent for no particular reason. And I can write the equation tangent of theta equals opposite over adjacent for theta. Now, in this particular case, 6.2 divided by 4 is the decimal you see here, 1.55. But now I'm trying to solve for an angle this time. The tangent of some angle I don't know is 1.55. One way that you could do this is by guess and check. You could take your calculator and type in tangent of 30, tangent of 40, tangent of 50, and keep typing in values of theta until you got an answer pretty close to 1.55, and then you would know what theta is. There's a little bit of a faster way, though, and that's using something called an inverse trigonometric function. Most calculators will have a what some students call tan minus 1, but is actually pronounced inverse tangent. And you can type in inverse tangent of any number and find the acute angle whose tangent is that number. Now, it's worth noting before we type this in a calculator, it's worth noting that the process of transforming a tangent equation into an inverse tangent equation, as shown here, is not universally a valid mathematical step. However, if you have knowledge, and I'm going to go a little bit beyond maybe the course that you're in here, but if you have knowledge that the angle you're looking for is an acute angle, meaning between 0 and 90, then this is, it turns out, a valid mathematical move. And if you look at the diagram, theta is an angle in a right triangle. It has to be an acute angle. If it's not the 90-degree angle, then the other two must be less than 90. And since theta is a positive and less than 90 angle, this move turns out to be one that you can use. But when you get into higher courses, you will not universally be able to convert a tangent equation into an inverse tangent equation. That being said, since we are in a situation we can do that, I can now just type inverse tangent of 1.55 into my calculator. Every calculator is different, so I won't get into the particular buttons to press here, but however it works on your calculator, typing that in and making sure you're in degree mode should yield an angle that's a decimal, but rounds to about 57 degrees. And now I know what theta is. So if you look at the diagram, the one thing I haven't found yet is alpha. I can find alpha now by just using the fact that the sum of the angles of a triangle is 180. And subtracting 57 and 90 from both sides will let me know that alpha is 33 degrees. Note that this is an approximation because theta, being 57, was also an approximation. But now I have the three things I was looking to solve for, and I'm done with this particular problem. Here's one last problem we can take a look at. Once again, notice that none of the angles are known, other than the 90, of course, and so this will be similar to the last problem. Step 1, label everything. I've called my leg C and my unknown angles delta and beta. Again, Greek letters are my tradition for, not mine, but I follow the tradition of Greek letters for angles, but you don't have to do that if Greek letters make you uncomfortable. But label everything however you like, and let's go about the business of solving. Once again, it wouldn't hurt to start with the Pythagorean theorem, leg squared plus leg squared equals hypotenuse squared. This will enable us to solve for C. Subtracting 4 squared from both sides and using the radical property, I can type that in a calculator and find out that C is 3. And now that I found out that C is 3, let's go about the business of finding delta and beta. We'll start with delta. I chose it for no particular reason, but you'll notice that I chose cosine. If you're wondering, how would I go about this? How would I know to choose cosine of delta to start with and not the tangent of beta or some other thing? Well, ultimately, you'll want to go back to writing out all 8 equations if there's ever any doubt of what should I use at this moment. But again, the goal is ultimately to be able to have sort of a sense. And there's no formal way I can explain that other than to say the more problems you do, the more sense you'll get about how to go about solving them. But I will share a little bit of my insight here. If you look at the diagram, and suppose we're trying to solve for delta first for no particular reason, we could have solved for beta first. But if we're trying to solve for delta first, notice that we know the adjacent side to delta, that's 4, and the hypotenuse 5 in the diagram. And since the cosine is the adjacent over the hypotenuse, it made sense to use the cosine. If you have no idea what I just said, don't worry. You can always write out all 8 equations for every single problem until you start to get a sense yourself of how to do less work. But I've written this out here, and I now want to know what delta is. Well, 4 divided by 5 is the decimal 0.8, and so I'm looking for something where the cosine of that thing is 0.8. I could do guess and check here. I could try the cosine of 20, the cosine of 30, the cosine of 35 until I got something that was approximately 0.8. Or, to avoid all that hassle, I could use the inverse cosine to solve here. Now again, that on your calculator, by the way, works out to 37. It's worth noting again that this process is not a valid process in future math classes, more than likely. But when you know that delta is an acute angle, one between 0 and 90, then this is a legitimate process. And since we know that, delta being one of the angles of a right triangle, in other words, then yes, you can go about this process. And finally, we can solve for beta by just using the sum of the angles equals 180 rule and find out what beta eventually is. And that completes this problem and this video on solving right triangles. Thank you so much for watching.